In this lecture, we will derive a system of equations for finding the least squares polynomial approximation for a continuous function f of x equals y over the closed interval from x equals a to x equals b. Let p sub n of x be the least squares polynomial approximation of degree n. Let p sub n of x be equal to a sub 0 plus a sub 1 times x all the way to a sub n times x to the nth power. If p sub n of x is the nth degree least squares polynomial approximation for f over the closed interval from a to b, then p sub n must minimize what is called the least squares error. Let us suppose that the least squares error is the quantity e. Then e equals the integral from a to b of the square of the difference between f and p sub n. This least squares error is just the square of the L2 norm of the difference between f and p sub n. In a more general setting, what we sometimes call the weighted least squares error has a weight factor w of x as part of the integrand. W is a given positive and continuous function on the closed interval from a to b. In this lecture, we derived a system of equations for finding p sub n for the specific case where w equals 1. In minimizing the least squares error, the coefficients a sub 0 all the way to a sub n are the unknowns that we are to solve for. If the least squares error e is minimized, then the partial derivative of e with respect to a sub I should be 0 for all I from 0 to n. And so we differentiate with respect to a sub I the integral from a to b of the square of the difference between f and p sub n. If f is a continuous function, then we should be able to get this derivative by differentiating the integrand with respect to a sub I, and then integrating the result with respect to x from x equals a to x equals b. In other words, we should be able to bring the differentiation inside the integral. The first part of the derivative of the integrand with respect to a sub I is 2 times the difference between f and p sub n of x. Not forgetting the chain rule, we still have to multiply this by the derivative of the difference between f of x and p sub n of x. F of x does not depend on a sub I. Only p sub n of x does. Hence, we still need to multiply by minus the derivative with respect to a sub I of p sub n of x. Since a sub I is the coefficient of x to the ith power in p sub n of x, minus the derivative with respect to a sub I of p sub n of x is minus x to the ith power. And so the derivative of e with respect to a sub I is minus 2 times the integral from a to b, with the integrand being the difference between f of x and p sub n of x times x to the ith power. At the minimum value of e, the derivative of e with respect to a sub I should equal 0. And so, for the system of equations for finding p sub n of x, we have the integral from a to b, with the integrand being the difference f of x minus p sub n of x, and then times x to the ith power. This integral is equal to 0 from I equals 0 to n. One can show that by using a Fourier series of orthogonal polynomials over the interval from x equals a to x equals b, that there is a unique solution to this system of equations.